Good evening, students. So, in last class, we have discussed about the valency bond theory. So, valency bond theory doesn't explain the so many properties of the complexes. So, let us discuss what are the failures of the VBT. So, VBT, it involves many assumptions. Means there is no exact proof. So, they all beliefs. So, he has assumed many things. So it is based on so many assumptions, and it does not give quantitative interpretation of magnetic data. So he said that the complex which is paramagnetic and which is diamagnetic. So but he doesn't calculated the mu values. So magnetic moment values, it doesn't give in the exact magnetic momentum of the complexes. So it is doesn't consider the quantitative interpretation of magnetic data. So it doesn't give the mu values. And next, it doesn't consider the ligand strength. So he doesn't explain why some complexes are paired up, means they are uh, violating the Hund's rule, and some complexes are not pairing. So the electrons are not pairing. That complexes, so why they are so paired up? The electrons are paired up in the presence of ligands. That he doesn't consider the strength of ligands. So it doesn't explain exact structure of four coordinated compounds. So in the case of coordination number 4, so either it may be sp3 hybridization or it may be dsp2 hybridization. So which complexes are exhibiting sp3, means tetrahedral structure, which complex is square planar? It doesn't explain the exact hybridization and structure of the four coordinated compounds. So here so many these failures are come across by the crystal field theory. So this theory has explained so many properties of the complexes. So it depends on the ionic nature of the complexes. So before crystal field theory, VBT theory assumed that there is a covalent bond formation between the metal orbital, and means overlapping between metal orbital and ligands orbital, that is completely covalent in nature. So covalent bonding. But crystal field theory explained about the ionic nature of the crystals. So let us see. So crystal field theory is an electrostatic model. So it is based on electrostatic attraction forces between positive ion and negative ion. So which consider the metal ligand bond to be as ionic bond. So VBT assumed the nature of bond between metal and ligand is covalent. But here this theory considered between metal ion and ligands there will be ionic bonding, means electrostatic force of attraction arising purely from electrostatic interactions between metal ion and ligands. So it explains both color and magnetic properties of many complex compounds. So this theory explained the color of the complexes and magnetic properties of the complexes. So let us see. So what are the postulates of crystal field theory? So this theory assumes that it considers the metal ions as cations, because after losing electron they will have positive charge. So the metal always loses electrons and it will have positive charge. This acts as cations. And negative ligands, so for example Cl minus, chloride, bromide, cyanide. So this negative ligands acts as anions. So for electrostatic interaction, there should be one cation and anion. So he considered metal ion as cation and negative ligands as anions. And what about neutral ligands? So he considered neutral ligands as the dipoles. So what is meant by dipole? So both plus end and minus end exist in the molecule. For example, ammonia is there, NH3. So nitrogen is more electronegative, it will have negative pole, and hydrogen will have positive pole. So he considered these poles. So he considered neutral ligands as the dipoles. That's why there is electrostatic attraction is there between metal cations and this negative pole. And next postulate is degeneracy of d orbitals. So the d orbitals doesn't have equal energy when ligands approaches to the metal cation. So these d orbitals are not degenerate, they will split into different energy levels. So before approaching of ligands, so before complex formation, the d orbitals will have same energy, but after when ligands approaches the metal ion, so they will split into different energy levels. That doesn't have degeneracy. So the degeneracy is breaked by the approach of ligands, so they will comes into different energy levels. Degeneracy means equal energy. So this equal energy split into high energy and low energy. So this splitting is due to approaching of ligands. So he explained why these splits. So this splitting of d orbitals depends on the crystal field, means which crystal field, octahedral field or tetrahedral field or a square planar field. So depends on the crystal field. And next strength of ligands. So means in the presence of strong ligands, how d orbitals are splits. So in the presence of weak ligands, how they are splitting. So means he considered the strength of ligands and approach of ligands. So means in which direction ligands are approaching the metal ion. Is there a x-axis or y-axis or in between axis or along the axis. So that approach of ligands depends on, so these three factors decides the splitting of d orbitals. Next, splitting of d orbitals in octahedral crystal field. So in octahedral field, so the octahedral field, if we consider this as axis, so this is z axis, x axis and y axis. So here ligands approaches in all x axis and y axis and z axis. So this is the, so means this is a symmetrical crystal field. So octahedral crystal field is a symmetrical crystal field. So next, so he explained the how d orbitals are splitting in the presence of octahedral crystal field. So metal forms metal ion, and this before approaching of ligands, this metal ion, it is having high stability, so it is more stable. So then, so here he considered this field, this crystal field as the spherical crystal field. So metal ion in spherical crystal field. So this is before approach of ligand. After approaching of ligand, this will become a spherical crystal field, and it is a symmetrical one because octahedral, in octahedral complex all axis, so the ligands approaches in all directions in equal, with equal strength. So that's why it is a symmetrical crystal field. So after approaching of ligands, so there is a repulsion between electrons. So after approaching of ligands, so this will face some repulsions. So there is both things are there. There is a attraction between plus and minus ions, and also there is a repulsion between this metal electrons. So metal will lose electron, they will have electrons. So there is a repulsion between electrons of metal and also electrons donated by ligand. So he considered both attraction and repulsion. So there is repulsion between electrons in metal field and electrons of ligands. So due to these repulsions, the d orbitals will, so they will face repulsions. So due to that repulsion, the electrons in d orbitals so will be splitted. In octahedral field, ligands approach along the x-axis, y-axis and z-axis. So how the ligands will approach in octahedral field? So they will approach along the axis. So along the direction of axis. So this is also along the axis. This is along the y-axis, z-axis and x-axis. So they approaches along the axis. So the d orbitals which lies along the axis will face high repulsions. So due to approach of ligands, he considered repulsions between the ligands and metal electrons. So these repulsions are faced by along the axis. When d orbitals are located along the axis, that will face more repulsions. So which orbitals lies in along the axis? So d orbitals are total 5 types. So the dx square, dy square, dxy, dyz, dzx, dx square, y square, dz square. So these are the different 5 types of d orbitals. So the orbitals which lies along the axis are dx square, y square and dz square. So this dx square and y square and dz square, these two orbitals will lies along the axis. So this is the structure of dx square, y square. So these orbital lobes are located along the axis, x-axis and y-axis. So this is structure of dx square, y square and dz square. So these orbitals are located along the z-axis. So these two orbitals will face more repulsions because ligands approaches along the axis. So that's why they will lifted into high energy. So they will have more energy. So the splitting of these energy levels into higher energy. So means dx square and dy square, dz square orbitals will split into high energy level. And then what are the remaining three orbitals? dxy, dyz and dxz. So these three orbitals, the lobes of these orbitals will lie in between axes. So they are not located along the axis. These orbitals will pointed into in between axis. So they will face less repulsions because ligands approaches along the axis. So they are somewhat far from ligands. So they will face less repulsions when compared to dx square, y square and dz square. So that's why dxy, dyz and dzx orbitals will face less repulsions and they will split into low energy level. So they will face more repulsions means the energy will be more and less repulsions means the energy will be decreased. So this is the splitting of d orbitals diagram. So this is potential energy on this y-axis and here stability on x-axis, energy on x-axis. So here d orbital, so this d orbitals in free metal ion. So there is no ligands. So before coming of ligands, they will have equal energy. So and less energy means more stable. So their potential energy is very less and they will be more stable. So after coming of ligands, so the energy of this d orbitals, so after ligands approaches to the metal ion, their energy will be rises. So the energy rises in octahedral crystal field. So due to the symmetrical nature and crystal field, due to the approach of ligands, there will be a crystal field. Crystal field is formed. Due to that crystal field, their energy will be rises. And after that, so the due to repulsions between ligands and metal electrons, so the energy levels are splits into different energy levels. Means here degeneracy is breaked. So they will split into different energy level. So this is the T2G level. So we have discussed. So the T2G orbitals, the dxy, dyz and dzx orbitals are called T2G level. So these three orbitals will face less repulsions. And here dz square and dx square y square. So these orbitals lies along the axis and they will face more repulsions and they will have more energy. So this higher energy level is called EG level. EG level has 2 orbitals and T2G level has 3 orbitals. These are T2G, xy, yz and zx are called T2G level, and this x square, y square and z square are called EG level. So due to this approaching of ligands and repulsions, so the energy levels will be, the d orbitals will be splitted into different energy levels, and this energy gap between this T2G level and EG level is called crystal field stabilization energy, delta naught, sorry, delta O. So here O means octahedral field. We are seeing splitting of d orbitals in octahedral field. So this delta O is called crystal field stabilization energy in octahedral field. So due to repulsions, the energy somewhat increases. If you see this line, so before approaching of ligand, after approaching of ligand, the energy will be raised. So when compared to this level, the T2G level and EG level will have somewhat raised energy. So this is due to repulsions. And then after this repulsions, so after this repulsions, their energy will be decreased. So they will come to, so this is the free metal ion energy level. So these are d orbitals, degeneracy is there. So all are having equal energy. But when the bonding process starts between ligands and metal ion, so the T2G and EG level will have less energy when compared to this one. So they will have, so like this. So this is the EG level and this is the T2G level. So this is due to repulsions, energy raised when compared to this D level. But after repulsions there is attraction because there is a bonding process starts between ligands and metal. So due to this bonding process, bonding occurs due to attractions. So after this repulsions, so the attractions will be dominated. So due to that attraction, the energy of T2G level and EG level decreases when compared to free metal ion. So that's why there is a stability, means energy is released means stability will be increases. So due to this attractions, there is a, the final crystal field complex will have the more stability.